To go along with our discussion of sorting algorithms, the other part of this usually is searching algorithms. So if I want to look for a value in an array, what are some different methods we can use to be able to search for elements? We're going to look at two. One is called the sequential search, and the other one is called the binary search. Again, we want to take a look at what exactly is the method, right? So what is the strategy in this search? And then we'd like to take a look at the efficiency of the search and really which is easier, faster, what have you. Okay, so we're going to take a look at both of these methods now, and then eventually we'll do some just practice questions to see kind of how it works and what the mechanics look like. Okay, the sequential search is probably the easiest out of all of these to explain. The sequential search is very straightforward. I'm looking for a value in the array. Let's say in this particular array, I'm looking for the value 42. We are basically going to start at the beginning of the array, and we're going to compare it. Compare the first element you see against the value you're looking for. If it's there, great, you found it. If it's not there, go to the next element. We are just going to go left to right, beginning to end, and we're going to see. So we're looking for 42. Is this 42? Nope, it's not. Is this 42? Nope, it's not. No, no, yes, we found it. Great, it's at element 4. It is very straightforward. Okay. In this case, the order doesn't matter. Whatever is going on, whatever the order of the values are, it doesn't necessarily matter, right? It doesn't have to. So we could just go until we hit the end of the list, and if it's there, great. If it's not, we'll say, nope, it's not here. If the list happens to be sorted in order, this is actually could be helpful to say that we will look until maybe if we were looking for the value 40, right? If this was sorted in order and we were going, and I saw 39 and then skipped to 42, if you knew that the array was in order, you could say, well, there's no sense of me searching element 5 and 6 because I know that the 40 doesn't exist because it's in order. All right, so there are kind of two ways you could do a sequential search. If they're not sorted, just go from start to end and keep checking to see is the next element in the array equal to the value I'm searching for. And if it's there, great. If it's not, and you hit the end of the array and haven't found it, well, it's not here. If the array is sorted from low to high or high to low, once you kind of pass where the element should have been, and it's not found, well, we can stop searching early because we know it's not going to be there. So this is called a sequential search. The best case scenario for the sequential search is that the key value you're looking for is in the first element. If it's element number 0, this takes one comparison, we're done. The worst case scenario is that the key is in the last element, or really it's not in the list at all, because every element would have to be compared. Right? So that's the worst case scenario. The slowest value, the slowest way this could run was if the value you're looking for is at the end of the array or not in the array at all, because then it would have to evaluate every single element. On average, we can say either it's going to take one comparison or all the comparisons. So we'll basically say that the average length of the search time is going to be the number of elements n divided by 2. So we'll just kind of split the difference in the middle. All right, so that's a sequential search. It is literally go left to right and check every single element. Is this the one we want? Nope. Is this the one we want? Nope. Is this the one we want? Yes, it is. So very straightforward. The binary search is a little bit more complicated. And this is another example of a divide and conquer algorithm. If you go back to the binary sort, right, they both happen to be called binary, but they're both divide and conquer algorithms. We'll show you kind of what we mean by that. In theory, with the divide and conquer algorithms, if there is a reason why I cannot have to search for every single element in the array, and I can start to eliminate large groups of elements, great, because that means I'm just going to have less elements to have to look through. Okay. In order for the binary search to work, the array must be sorted in ascending order. So this array would not work the way it is. This whole algorithm is based on the fact that the array is sorted. If it's not, you'll have to sort it first. Okay. So here we're going to put the array in order. Okay. Let's again say that we're looking for that 42. Okay. What we are basically going to do is, because the array is in order, we are going to start in the middle of the array. Okay? So we're going to calculate where the middle of the array is. And basically what you'll do is whatever is in the array here, we're going to take the lowest index, add it to the highest index. So if 0 plus 6 is 6, divide by 2, and this will find me the midpoint. Okay? So the left end and the right end of the search area, divide by 2 to get you to the midpoint. Okay. Then we ask the question, is this the value? Is the pointer at the value we're looking for? In this case, no, it's not. If it was, great, the sort would be done. If it's not, the question really becomes, is the search term that we're looking for higher or lower than the midpoint? What we're trying to do is we're trying to eliminate immediately half of the number of elements in the array. Because if I know that element number 3 in this example is not the value I'm looking for, then what's the point of searching anything lower than it? We don't need to. We can totally scrap the entire left or right side of the array. So in this case, the 42 is higher than 39. So there is no reason to look at the 39 or to the left of it, because we know it's not there. And then we will now basically ignore the shaded element here. And now this is the new array that we have to search. We're only going to search these 3 elements anymore. We'll set the midpoint again. The low index is 4. The high index is 6. That's 10. Divided by 2 is 5. So the midpoint is now 5. Is this the value we're looking for? Is 43 42? No, it's not. The value we're looking for is to the left of this, so we're going to basically ignore everything on the right. The low index is 4, the high index is 4, that's 8 divided by 2. Now the midpoint is at 4. Is this the value? Yes, it is. Okay, so really, in 3 comparisons, we found the element. Back up here for a second. There's comparison 1. Is element 3 equal to the search term? Is element 5 equal to the search term? Element 4 equal to the search term. 3 comparisons, we were able to find what we needed. Okay. So the beauty of this is that at any point in time, we are really only searching half of the unsearched elements. So we can very easily take a very large array and knock it down into only a couple of comparisons. But again, in order to do this, the array must be sorted ahead of time. The best case scenario in this search is that the element's found on the first try. It's sitting exactly in the middle of the array. Worst case scenario is that the search term is not in the list, or it is at the end of the array, and that way it would take the most number of comparisons in order to get there. So one of the questions I've often seen asked is, let's say I gave you an array of some size. How can we figure out how many comparisons would it take to be able to either find, at the worst case scenario, how many comparisons would it take to find the search term or find that it's not there? Worst case scenario. And here's a little shortcut. We want to take the number of elements in the array, okay? And we're going to compare it against the powers of 2. And you're going to round up to the next power of 2. And the exponent will tell you how many comparisons need to be there. Let me illustrate that for you. I'll start at the top here. Let's say I gave you an array that has 8 elements in it. 8 is really equal to 2 to the third power. The maximum number of comparisons you will get is going to be 3. In this case, let's assume that there are 20 elements in the array. I want to see where does 20 fall in the powers of 2. You might want to eventually memorize these numbers. 1, 2, 4, 8, 16, 32, 64. If we kept going, 128, 256, 512, 10, 1024, 2048, you start to memorize the numbers after a while. But we know that the n is equal to 20. So 20 would kind of sit here, right? So the next base 2 number above 20 is 32. The number of comparisons to inspect a 20 element array would be 5. Take the exponent. Okay, so if you want to know how many comparisons an array search would take, find the number, round up to its next power of 2, and take the exponent, and that'll be the number of comparisons it takes. So the binary search is really great in a divide and conquer algorithm because it's going to dramatically drop down the number of times you need to search through the array. And think of it, if we had a 1,000 element array, right? After the first time we search for it, we search for the term, immediately 500 elements are going to come off our search plate. Immediately. And then if we don't find it on the next search, another 250 are going to come off the list. And then another 125 are going to come off the list. So every time the search iterates, we immediately knock out half of the elements that we don't have to search. For this reason, the binary search, any divide and conquer algorithm tends to be more efficient, or definitely going to be faster, because you don't have to compare every single element in the array. We can easily knock things out. Okay, so that's a little bit about the binary search and the sequential search, and we will put some questions out there for you to maybe look at to see what exactly this would look like. And again, you want to just be more familiar with the mechanics of the search algorithm. How exactly does it work? And then we want to know a little bit about how to find its efficiency.